One of the most frustrating things when you're starting to learn chemistry is that you start to feel really good about your understanding, and then chemistry always throws curveballs at you. This is one of those curveballs. It's like, I'm feeling really good about drawing Lewis structures. I'm getting really good at it. And now I'm going to tell you that sometimes there are exceptions to those rules that you've been learning about drawing Lewis structures. I apologize. I don't make this up, but I am going to teach you how to deal with it. And I'm going to teach you how to be successful when you're drawing Lewis structures if you run into something that has what's called an expanded or an incomplete octet. These are the rules that I put up for every lesson on Lewis structures. If you don't have them written down, pause the video, write them down. You're going to need them. And we're going to continue on. The exceptions to the rule then. There are things, now we've learned about the octet rule, right? That's when every atom has 8 valence electrons around it when we're done drawing our Lewis structures. Except for hydrogen, it's okay only having 2. But everything else should have 8 valence electrons. And now we're going to find out some have an expanded octet. What do you suppose that means? They're going to have more than 8 valence electrons when we're done building our structure. And some will have an incomplete octet. That means they won't even... Now, I can't confirm or guarantee that whoever you're learning chemistry with, or if you're learning it on your own, is going to tell you if the Lewis structure you're about to draw has an expanded or an incomplete octet. But if you're following along with me, and if I'm your teacher in your class, I will always tell you if the molecule is an exception to the octet rule. Here's why. There's nothing more frustrating than trying to learn how to do something new, like drawing Lewis structures, and then not knowing if there's an exception. Like, am I drawing this correctly? Because I don't know if it's an exception or not. So if you're sticking with me through my lessons and you're using my worksheets and my practices at Beals Science and the Beals Science School, or down there in the description, I'm always going to tell you if it's an exception to the rule because I want you to be successful. As you get really good at this, you'll know when they're an exception. You're going to do just fine down the road, but that's after you've learned a little more about chemistry. So in all the practice problems we're going to do together, if I don't tell you it's an exception, you just follow the rules that were on the last slide. Well, let's go over it one more time just to make sure you understand. How are you going to know if a molecule has an incomplete or an expanded octet? You won't, which is why I'm going to tell you that it is an exception to the rule. I might not tell you that it's an incomplete or it's an expanded. I'm just going to tell you that it's an exception to the octet rule. And believe me, you'll be able to figure out if it's expanded or incomplete if you just follow the steps I'm going to show you. For an expanded octet then, some representative elements may form more bonds or have more lone pairs of electrons on the central atom than we would expect. That's called an expanded octet. It's kind of breaking the rules. The reason it's breaking the rules is that atoms and electrons, they don't care about our rules. We come up with rules as chemists and chemistry teachers to help you understand chemistry. But then as you start to understand more chemistry, you realize, wow, the reason there's exceptions to the rules is that electrons don't care about our rules. We just made them up to help you learn. Another term for these are hypervalent electrons. A good example of that is this one right here, sulfur hexafluoride. I've just drawn the skeleton structure for that to leave the electrons off. But you should be looking at that going, wow, that sulfur has way too many. It should only have 8 electrons. And it has 2, 4, 6, 8, 10, 12. When we talk about expanded and incomplete octets, it's only going to be for the central atom. Don't forget that. It won't be for the ones out here. There are common elements that exhibit expanded octets. I'm only showing these because if you're working with a teacher or a professor that's expecting you to be able to recognize them, then this is a good starting point. If you have a central atom that's sulfur, phosphorus, silicon, or chlorine, it is possible that it will have an expanded octet, but it depends on what it's bonding to. And that combination will determine if it has an expanded octet or not. There is a way to kind of help figure this out called formal charge, but a lot of it involves just memorizing the combinations where this is going to happen. If you were in my chemistry class for introductory chemistry, we don't memorize these. We just learn how to be able to draw them correctly. For an incomplete octet, sometimes they, again, won't have 8 valence electrons. They'll have fewer than 8. And they're perfectly fine having fewer than 8. Boron trifluoride is a good example of that. And there are some common ones, boron, beryllium, aluminum. There are others as well. But when I teach students, how to memorize which ones are going to be exceptions to these rules, Those are the ones, boron, beryllium, and aluminum. And if you really want that, I do have more lessons for more advanced chemistry. There'll be links in the description to help you out. Otherwise, just follow along. You're going to do great. The best way to learn these is to do examples together. Look, this is an exception to the octet rule, which makes sense because that's what we're learning about right now. But if you've been following along on our lessons, there's nothing different about the 6 steps. They're all the same. So how am I going to know, or how do I draw this with an expanded or an incomplete octet? Let's do it like normal and we'll see. Number 1, we're going to add up all the valence electrons. I've got beryllium in my compound or in my molecule, 1 beryllium. And I've got hydrogen. We have 2 of those. I can see that. I find beryllium over here on my periodic table. Looks like right here. And it's in group 1, 2A. So it's got 2 valence electrons times 1 because there's only 1 beryllium coming to our party. And that gives us 2 electrons. All right, let's find our hydrogen right here. That's easy. It's in group 1A. So each hydrogen has 1 valence electron, but there are 2 in our compound. So that's 2 electrons. We add them up and we get 4 electrons. We need to add or subtract to reach the formal charge. The formal charge would be if there's a plus or a minus up here. It doesn't have that, so we're done with number 1. We build the skeleton structure. We're going to go ahead and put the one with the lowest electronegativity in the middle. We don't even need to look it up. If you remember a rule I told you a long time ago, hydrogen will never be the center of any molecule because it can only make 1 bond, which leaves beryllium. That's going to be the center of our molecule. And I don't know where the hydrogens go. Let's just say they go there for now, and then we can adjust them down the road if we need to. Here is our skeleton structure because we have our 2 hydrogens bonded to our central beryllium. Then we add the electrons around the outside of the molecule till we've used them all up that we calculated right here. But look, I've already used 4 electrons. I can't add any more electrons, so I can't, well, what do I... Now, if you've followed along with me in the past and we have an unhappy central atom, because notice this beryllium only has 4 electrons around it, and we would think, according to the octet rule, it should have 8. But we don't have any more and hydrogen doesn't have any electrons to share. That's why this is an exception to the octet rule. This one's okay existing that way because some of them, well, they just don't care about our rules, and it's fine being able to exist that way. And a lot of it has to do with something we talked about in several lessons back, is that beryllium, because it's just filling up its first energy level, and it's going to be totally fine. We don't have a formal charge. This does not have resonance structures because there's no double bond that we need to try to figure out where to put it. And we just double checked our answer. So there's our beryllium hydride. Phosphorus pentachloride is an exception to the octet rule. That's why I've chosen it as our next example. Now let's work through all of our steps or all of our rules. We can see we have 1 phosphorus. We have 5 chlorine. I find phosphorus to see how many valence electrons our phosphorus have. I can see it right here. It's in group 1, 2, 3, 4, 5. So it has 5 valence electrons times 1 phosphorus that's going to show up. Chlorine is way over here. It's in group 7A. So it has 7 valence electrons, but 5 of them in our compound. 7 times 5 is 35. I add them up. 5 plus 35 is 40. Wow, there's a lot of electrons on this one. Does it have a formal charge? No. Let's build our skeleton structure. What's going to go in the center? Lowest electronegativity. Phosphorus is further away from this corner where everything has a high electronegativity, so it will be the center. Let me put our phosphorus there. I need to branch 5 things off of this. I need to bond 5 chlorines. So I'll just go ahead and kind of put 5 on here, and this is where you should be going, this is definitely a problem because that phosphorus, the way I have it drawn right now, is going to have way more than 8 valence electrons. It has 2, 4, 6, 8, 10, but because I'm reminding you that this is one of the exceptions to the octet rule, you're going to say, okay, I guess I'll let it slide this time because Mr. Beals told me that this is an exception. We built the skeleton structure. Now we're going to add electrons until we reach 40. I need to count up how many I've used. 2, 4, 6, 8, 10. Let's start here. 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. There we go. I've used up all 40. Add brackets if it has a formal charge. It does not. Resonance structures. Nope. There's no double bonds where we needed to figure out, should I double bond here or should I double bond there? And when we're checking our answer, it should throw up some red flags. We should say, all these chlorines have 8, so they're perfectly fine and happy. But our phosphorus has more electrons than we would expect. It has 10. But because we were told that this is an exception to the octet rule, we can stop here and say that that is the correct Lewis structure for phosphorus pentachloride. And if you want more practice with all the different things, I have links down there in the description that'll take you to worksheets, that'll take you to BealsScienceSchool.com, take you to BealsScience.com, where I have lots of other resources for you to practice more and more of these. There's one more thing that I like to cover in my chemistry class before we kind of close the book on Lewis structures. And that is when we have multiple central atoms, like especially where we have chains of carbons with things branching off of it. And that's kind of, in my class, the first real introduction to organic chemistry. If you're interested in that, go ahead and follow the link down there in the description. If you're looking for other things, there's lots of stuff popping up on the screen, or come on over to BealsScienceSchool.com and learn right along with me. And I'm just here to remind you to keep on learning.